Hello everyone, I hope everybody is fine and healthy. This lecture is about solving rational inequalities. Uh, Most likely you have to review this video lecture 2 or 3 times, and I hope you will understand the methods that are discussed here. We have a rational inequality. It says x over x squared minus 2x minus 3 less than or equal to 1 over x plus 3. On both sides you see some rational expressions. The first thing we do, we are going to simplify this inequality a little bit by transposing all the terms to one side of the equation so that we end up with 0 on the other side. So this is what we get. So we have negative 1 over x plus 3 on the left-hand side. We never ever cross multiply inequalities. This is extremely important. Pause the video right now, make a note of it. If it's a rational equation, you may cross multiply, okay, by studying the restrictions. But in case of inequalities, you never cross multiply. So now we have to combine these two rational expressions on the left-hand side by finding the lowest common denominator. And perhaps if we factor this quadratic trinomial, that's going to be x minus 3 times x plus 1. So right away we see that none of these two factors is the same as x plus 3. So we're going to find the lowest common denominator, LCD. So we get x minus 3 times x plus 1 times x plus 3. So we get x plus 3, and then minus the product, which is actually x squared plus 2x plus 3 less than or equal to 0. I have no doubt that you will do these questions by yourselves later on. And now we have to simplify the numerator. So x squared minus x squared, they cancel out each other. We have 3x and 2x, that's giving us 5x, and then plus 3 in the numerator. And the denominator remains unchanged. So this is what we end up with, okay? Now this expression that is less than or equal to 0 on the left-hand side, the simplified rational expression, I'm going to call this r of x. Or you can call it f of x or whatever function name you want to give it. So this is r of x, so that we can refer to that later on. Okay, so we ended up with one rational expression or one rational function which is less than or equal to 0. Obviously, it has a numerator, it has a denominator. Very quickly, we're going to find out the roots of the numerator and the denominator. By setting the numerator equal to 0, we can set 5x plus 3 equal to 0, and you can solve for x, and that will be negative 3 over 5. So the zeros of the numerator would be x equals negative 3 over 5. And for the zeros of the denominator, it's very clear that we have 3 zeros. One is x equals 3, one is x equals negative 3, and one is x equals negative 1. There are 3 zeros in the denominator, 1 0 in the numerator. Now, these 4 zeros of the numerator and the denominator divide the real numbers into 5 intervals as follows. Now, I'm going to use this chart method first of all. So, as I said, we have 4 zeros in the numerator and denominator, and these numbers, negative 3, negative 1, 3, negative 3 over 5, they divide the number line into 5 intervals. This is the first interval, values of x less than negative 3. This is the second interval, values of x between negative 3 and negative 1. This is the third interval, negative 1 up to negative 3 over 5. And this is the next one from negative 3 over 5 up to 3. So that's the fourth one, 1, 2, 3, 4. And x value is more than 3, well, that would be the fifth interval that is generated by these 4 zeros of the numerator and the denominator. Now, what we do, all these factors we have only one factor in the numerator, 3 in the denominator. So that's 4. 1, 2, 3, 4. We list them all on the left-hand corner. And for the last row, I just put r of x, which means the whole rational expression on the left-hand side of the inequality. So now I have to identify the plus minus sign of these different factors in my chart. First, I'll go after the zeros, just like we did with the polynomials. If x is negative 3 over 5, 5x plus 3 will be 0. if x is 3, then x minus 3 will have a 0 value. If x is negative 3, x plus 3 will be 0. If x is negative 1, x plus 1 will be 0. And if x is equal to the root of the numerator, then r of x will be 0 because its numerator is equal to 0. And if any of the roots of the denominator are taken into account, then those are causing the denominator to be 0. That means that r of x, the rational expression or rational function, will be undefined at those zeros of the denominator. Very clear. So I'm going to put infinity symbol here just to indicate this. Now, if x is larger than negative 3 over 5, we have a plus sign for 5x plus 3. But if x is a value less than negative 3 over 5, such as negative 1, such as negative, any value between negative 3 over 5 and negative 1, or any value less than negative 1, this 5x plus 1 factor will have a negative sign. X minus 3 is plus on the right, it's negative on the left. X plus 3 is positive on the right-hand side. If x values are more than negative 3, they would cause x plus 3 to have a positive value. And if x is less than negative 3, such as negative 5, 6, 7, 10 million, then x plus 3 will have a negative sign or negative value. That's why I put the negative sign in the box. X plus 1 is 0, we said it. So to the right is positive, to the left it's negative. So these are the plus minus signs of the 4 factors, 3 of which are in the denominator and 1 is in the numerator. So negative divided by negative is positive. Positive times negative is negative. Negative times negative is positive. So we end up with a positive sign overall for the r of x in the first interval. Negative divided by negative is positive. Positive times positive is positive. Positive times negative is negative. So that becomes negative. Similarly, we have plus sign, minus sign, plus sign. So over different intervals, we did identify the sign of r of x. Okay, we want r of x to be less than or equal to 0. Less than 0 means negative, and negative means this part and that part. Okay, so the positive parts we do not, care about this part. We don't care about this part. We're not interested in the positive part. We are interested in less than 0, less than or equal to 0. So we're going to take into account x values between negative 3 and negative 1 exclusive, and x values between 3 and negative 3 over 5, including negative 3 over 5, because at negative 3 over 5, r of x is 0, of course. So now it's time to write our solution set. SS stands for solution set. So I'm going to say x is between negative 1 and negative 3 exclusive, or it is between 3 and negative 3 over 5, including negative 3 over 5, but excluding 3. Okay, now in interval notation, you can write this in the form of the union of 2 intervals. Okay, that's possible to do it. Regarding graphing the solution set, we can say the interval between negative 3 and negative 1 would be this distance right there. We can draw a line, solid line. We have empty circles over the holes at negative 3 and negative 1 because we have to exclude them. And then negative 3 over 5 is starting from here, and it goes all the way up to 3, and it excludes 3, but includes negative 3 over 5. So this would be the graph of the solution set, actually. So this is like so-called chart method. Okay, there's another method that you can use to solve rational inequalities, and that's called test value method. In this test value method, we do the preliminary work of finding that r of x on the left-hand side of the inequality, and then we find the zeros of the denominator, zeros of the numerator, same thing we did, so those parts are the same. But instead of constructing a chart like this, of course nothing is wrong with that, I'm just showing you different methods out there, and you can use any method you want. Instead of that, we are using something we call it test value method. So I'm dividing those intervals, like I'm dividing the set of real numbers into different intervals. We have 1, 2, 3, 4, 5 intervals here, just like those intervals. The first one is from negative infinity up to negative 3, and I select a test value. Okay, what will be the test value I select within that interval? So I can select any number, between any number less than negative 3, basically. Okay, So you can select -4, -5, -11, whatever you want. So my test value is x equals -4, I select. Now if x is -4, I wonder what the numerator will be. It would be 5 times -4, which is -20, plus 3, and that's -17. Now, we don't care about the value of the number -17 or -18 or whatever. We care about the sign only. So the numerator has a negative sign. That's what we are interested in. And the denominator, if you plug in -4, so this expression will be negative, that will be negative, this will be negative. So we'll have 3 negative expressions in the denominator, causing a product to be negative. So that means that the denominator will also have a negative sign if x is -4. And -4 is the test value that arbitrarily I selected within the first interval. So negative divided by negative is positive, which means that r of x will have a positive sign, right, in that interval. Now, another test value between -3 and -1, I select -2, for example, and I plug it in the numerator, I get a negative answer. Plug it in the denominator will be positive, because think about it. If you plug in -2 here, that would be negative. This would be negative, but that would be positive. So negative times negative is positive. So that's why we say the denominator will have a positive sign. And negative divided by positive would be negative eventually. So for the next interval, I select some test value, -4/5, for example, and I find the sign of the numerator and the denominator like before, and then when you divide them, you end up with a positive sign. The test value I select between 3 and -3/5 would be x equals 1. You can select x equals 2 or 2.5, whatever, is easier. Then I end up with a plus sign for the numerator, and the denominator will become negative, causing the whole rational expression to be negative. And for the last one, x equals 4, I select. I could have selected 5, 6, or whatever you want, you could have. And both the numerator and the denominator will have a positive sign, causing r of x to be positive. So here, we see that we want r of x to be negative. So this part must be taken into account, and that part must be taken into account. So over what interval is this happening? Over what interval or intervals the rational expression r of x is negative? Well, one is here, one is there. So I wrote here -3 to -1, and then -3/5 up to 3, okay? And I took the union to combine the two intervals. And of course, needless to say, the zero equality case, goes with the case when x equals -5/3, -3/5, which is the 0 of the numerator. So I have to include -3/5. So you see that by this test value method, you can just find the sign of the numerator, sign of the denominator, and divide them to find the sign of the whole rational expression, okay? Or if you don't like this method, you can always use the chart method. As you clearly see, they both have exactly the same final answer, okay? The answers are perfectly matching. Method number 3. Method number 3 is by using graphing method, okay? These two methods were algebraic methods I discussed. Now we have this graphing method. So in the graphing method, if you have access to graphing software, or if you're good in graphing, you can draw the graph of the rational function, which is sitting there on the left-hand side of the inequality, and on the other side we have 0. You can draw the graph of it. You know that there are 3 vertical asymptotes. One is at x equals -1, one is x at x equals -3, and one is x equals +3. These are the zeros of the denominator that would translate into equations of vertical asymptotes for the rational function. We do have a horizontal asymptote, which is y equals 0. I labeled it here, and that is the x-axis equation, okay? So we have 4 asymptotes, 3 vertical, 1 horizontal for this rational function, okay? And when you draw the graph, okay, and you have your x-intercept, y-intercept, it's not that hard to plug in 0 here, and then find out what the y-intercept is. It will be -1/3. And to find the x-intercept, you set y equal to 0, or r of x equal to 0, and you find -3/5. That's the x-intercepts where the graph intersects the x-axis. And when you draw the graph of the function, you look for parts of the graph or intervals in the graph where r of x is less than or equal to 0, meaning that it's negative, meaning that the graph is below the x-axis in the negative region. So here I say the graph is below the x-axis over this interval. So look at the graph. Up to -3, the whole graph is above the x-axis in the positive region, which means that r of x is positive. But then between -3 and -1, we have r of x, which is negative, because it's below the x-axis clearly. But then from -1 to -3/5, again, the graph is on the right side of the vertical asymptote, and it's decreasing above the x-axis in the positive region. But then after the x-intercept, you see that the graph is again below the x-axis in the negative region. So that happens up to x equals 3. So we say from -3/5 up to 3, the graph is below the x-axis, and after 3, again, the graph is up above the x-axis. So by just looking at the graph and find out intervals over which the graph is above or below the x-axis, we can easily write the very final answer in one shot, instead of going over all those algebraic calculations and plus signs and minus signs and everything. By looking at the graph, okay, and by knowing if r of x is supposed to be negative or positive, we can easily find the interval or intervals over which r of x is negative. So that was the graphing method. This was the chart method. This was the test value method. So 3 methods was discussed here. 3 methods discussed, and hopefully you will learn these 3 methods. You don't have to solve a question 3 different ways, but I just want you to know about the existence of these methods. Whichever method you find it easy, whichever you are comfortable with, whichever you understand better, you can always use that method. Okay. Now it's time for you. It's your turn to sit down and do a lot of practice questions, and maybe practice these methods to become good at them. Thank you very much.